In this video, let us have a look at what happens when a capacitor is connected to an AC source. So this right here is a symbol for an AC source, and this here is a capacitor. Now in this for this particular explanation, we are going to assume that this whole circuit has negligible or zero resistance, and also it has no inductance, which is clear because it has no inductor in it, and therefore it only has a given capacitance, the capacitance of this capacitor, and thus this would be called a purely capacitive circuit. And yeah, so let's just start. So we can first of all apply Kirchhoff's loop rule, which states that the potential gained at the source should equal the potential dropped across the whole circuit, across any one given loop. Here we have only a single loop, and so we can write that in this form: V, which is the source voltage, the AC source voltage, that should equal the potential drop in the whole circuit, and we have only one place where we can have some potential drop, which is this capacitor. And what would be the potential drop across the plates of a capacitor? Well, that should be equal to the potential difference across the capacitor plates, and we know that the potential difference across the plates of a capacitor is given by the equation capacitance equals charge stored divided by the potential difference, right there. So what I can do is I can take this V on the other side, right there, and I can bring the C from the other side and bring it here, right? I just shift it and I get my V. So I know that the potential difference across the plates is Q by V, or the charge stored divided by the capacitance. So I can write that there and remove this relation here. They look similar, although yeah. So this is my source voltage. Now because this is an AC source, the source voltage is also alternating, or rather changing with time, and so we can write that in the expression by using the expression voltage at any incident time equals the peak voltage times sine omega t, and we know that where this thing comes from. So I can use this and put it in here, and what I get is Vm equals really sorry, I can put that in there, and I get Vm sine omega t equals Q by C, right? And now so yeah, I get right there. Now I wish to figure out the current in this circuit. So before that, I'll just quickly do one single step. What I can do is I can shift the C to that side, and what I get is an expression for the charge stored at any instant in time on either of the capacitor plates. So I can shift the C that side and also flip the equation this way. So I'll just shift the C on that side. I get C, or let's just do that here. I can remove the C from here and shift it here, and now if I flip the equation, I get Q equals CVM sine omega t. And now what I want is the current in the circuit. Now what is current? Current is nothing but the rate of flow of charge through the circuit, and the rate at which charge is flowing through the circuit is also equal to the rate at which charge is being deposited at either of the capacitor plates, right? And so if I find the rate of change of charge, rate at which charge is being deposited at the plate, what I get is the rate at which charge is flowing through the circuit, which is nothing but the current, right? So I can differentiate both the sides of this equation to find the rate of change of Q, or rate of change of charge, or rather rate at which charge is being deposited at the plates, and I get is dq. What I get is dq by dt, a small change in the charge stored divided by a small change in time. That equals this whole thing, CVM sine omega t, a small change in this whole thing with respect to a small change in time. I hope that fits perfect. And I know that the rate of change of rate at which charge is flowing is nothing but the current, so I can replace that whole term with I. Now I need to remove all this. I hope you've noted it down because I don't have space to do the next steps. Yeah, So I have an expression for charge current that equals rate of change of this whole thing with respect to time. Now I know the capacitance of this whole capacitor is constant. Also the peak voltage is a constant, so I can pull those two variables out because they're constant. I can pull them out of the derivative, and what I get is, I hope that fits. Yeah, I equals CVM multiplied by the rate of change of sine omega t dt, right? And now I know that the rate, so the derivative of sine of something is nothing but cos of something. But so what I can do is I can apply the chain rule. I'll just show you how that's done. I can write the whole thing as CVM rate of change of sine of something. So first let me just differentiate it with respect to that something, omega t, which is omega t, and then I can multiply this with d omega t by dt. So nothing, I've just multiplied the numerator with d omega t and the denominator with d omega t, and nothing, I've added nothing extra. And by doing that, what I get is d the rate of change of sine of something, or rather a small change in sine of something divided by a small change in that particular something, multiplied by d omega t divided by dt. And so I can now easily differentiate both those things. Let me remove this, and now if I write the expression for current, I get CVM, the rate of, so the derivative of sine of something is cos of that particular something, which is omega t in this case, multiplied by d omega t. Omega is a constant, I can pull that out, and what I'm left with is dt by dt, which simply cancel out. So I'm left with only that omega here, and yeah, that's pretty much it. Now what I can do is I can simply apply the identity. So I know that, I hope you remember this identity, cos theta equals sin theta plus 90, sin theta plus 90, or 90 can be written as pi by 2, and I'll apply this particular identity here. So if I just have I have enough space, so I can write this whole thing as I equals, so first let me write all the constants. Omega is a constant, so let me shift it that side. So what I can do is I can write it as omega CVM. Those three are the constants, omega CVM. And now instead of writing cos omega t, I can use this identity cos theta, where theta is my omega t. Instead of writing cos omega t, I can write sin omega t plus pi by 2. So I'll just write it as sin. So instead of writing theta, I'll write omega t, that's my theta in this case, plus pi by 2. And yeah, I am there. Let me remove everything else because yeah, just to make it a bit less messy. And yeah, now I've got my expression for current, which is I'll just put it here. I equals omega c Vm sine omega t plus pi by 2. Yeah, so that is my expression for the current at any point in time. And if you compare it with the general equation of current in an AC circuit, I equals the peak current equals the peak current times sine omega t. Let's ignore this pi by 2 for now, I'll deal with that later. But you can see that this whole term here is analogous to Im, so obviously this whole term would represent the peak current, and yeah, that is true. This whole term here is nothing but the peak current, so I can write the peak current Im as omega CVM. So instead of writing this whole thing, I can simplify this as simplify the whole equation by writing it as the current in the whole circuit at any point in time equals, so in omega c Vm, which is nothing but the peak current times sine omega t plus pi by 2. And yeah, that is my equation for current in this particular circuit. an alternating source connected to a capacitor, and this is my expression for the peak current. And now just to be a little manipulative, what I can also write this as Vm. So I can also write this whole thing as Im equals Vm divided by this fraction. So I hope you realize that this equation and that equation is the same, because when I divide Vm by this whole thing, I'll have to take the reciprocal of this and multiply it, and I would get nothing but Vm into omega c, and that's it. So why am I writing it this way? Well, I'll just show you in a moment. So Vm divided by 1 by omega c, or rather I can write the whole thing in the form of a fraction. So Vm divided by 1 by omega c, or rather Vm divided by 1 by omega c. So I can write this in this form, and when I write it in this particular form right here, this form, this seems pretty much similar to the form of our Ohm's law, which is nothing but the current. So this would be the case of a resistor connected to an AC source, which you've dealt with earlier, and in that case we had Im equals the voltage, the peak voltage, divided by the resistance. And if you see, we have Im there, Vm there, Vm there, and this whole term here, I by omega c, is analogous to the resistance in the case of a resistor. So this thing here is what is resisting or controlling the flow of current in our circuit, because obviously it has no resistance, so otherwise it should have blown up. So something is controlling the value of current, and that is nothing but this factor here, I by omega c. And yeah, so because that is analogous to the resistance in resistive circuit, we call, but this is not a resistive circuit, so we call this value here I by omega c. Let me make some space to write that. We call this the capacitive reactance of the circuit, and it is represented by the this symbol xc, because it is a capacitor, it's capacitive reactance xc. And yeah, xc is equal to this whole term 1 by omega c. And this is pretty much similar to the previous case of capacitive, so inductive reactance, which was represented by xl, for L for that the symbol of capacitance, xl. And yeah, that's pretty much it. Now one last thing that I'd like to add in this here is that so this equation here simply tells me that the higher capacitance that I have, so remember, if I have a higher value of capacitive reactance, it simply means that, so I can write this whole equation as Im equals Vm by xc, right? So it simply means that if I have a higher capacitive reactance, I'll get a lower current for a given source voltage, and that simply means, so this xc is nothing but opposing current. It is trying to reduce the value of current, and the higher the value of capacitive reactance, the lower current I get. And so in this particular equation here, so we can see that a larger capacitor, a capacitor with a higher capacitance, should offer a lower capacitive reactance, which means a larger capacitor or a capacitor with the larger capacitance would allow more current to flow. And why is that so? Well, that is so because so if you think, what is it that is stopping the current or opposing the current? Well, it is the potential difference that is being created here, or the so if you have it is the charge accumulation that is trying to oppose the flow of current, right? So if you have a capacitor with a large capacitance, more current can flow because the capacitor can accommodate more charge for a given potential difference across the capacitor. So I hope you are getting the idea. For a given potential difference across the plates, a capacitor with a larger capacitance can hold a larger amount of charge which means we can have a larger current flowing, because if we have a larger current flowing, we'll get more rate of change of, we will get more charge flowing through the circuit. And because it's a larger capacitor, it has a large capacitance, it can store that charge, so we can get a larger current as compared to a capacitor with smaller current, with a smaller capacitance. Now coming to the second term here, omega, that simply means how quickly the current is changing its direction. If it is changing the direction very quickly, the charge will not get enough time to get stored on the capacitor. So let's say the current is flowing in this direction first of all, so you'll get some positive charge being accumulated here, and some negative charge getting accumulated here. Now if the current is changing directions very quickly, as soon as we get some charge accumulation here, the current simply flips its direction, and then the polarity would switch. The charges would, now positive charge would be getting accumulated on this side and negative on that side, and then again it switches its direction. So the charge does not get enough time to get accumulated, and a higher amount of current can flow. But if the frequency of the source voltage is low, which means the current is changing its direction after a longer period of time, so in that case the charge would get a larger time, more time to get stored, and we cannot get that much amount of current to flow in the circuit. So that is the basic intuitive idea of this equation, why capacitive reactance depends on omega and C. And yeah, that is pretty much it in this particular video.